This is the last seat, right?
Yep.
Still got some guests hanging into the last minute. So let's get started.
Okay. All right. Good evening, everyone. We're Team 7, Team MoIST. Is the mic not working? It is working? Okay. Thank you. All right. My name is Ryan Alcorn. I'm the project manager. I'm joined today by Josh Fitch, Francesch, and Simon Sasin, representing our team. We're going to discuss our project background, then our orbit selection, followed by constellation performance characterization, data and link budgets, system operating modes, subsystem component selection, CAD overview, launch vehicle selection, cost model, space environment, and finally, a risk overview. First, for some project background with Snoopy, which is what our project is based off of. You can see Snoopy collects the root zone soil moisture, surface soil moisture, and snow water equivalent data with both a directed signal and a reflected signal off the transmitting P-band constellation. Our mission was based off of those requirements with the addition of a freeze-thaw requirement. And these also have specific latitude ranges and revisit requirements that our mission will have to meet. And now Josh is going to discuss our orbit selection to show how we met those. So a major component of this mission was obviously the design of the constellation orbits. To kind of start off with the design of these orbits, we looked at kind of very, very high level first order algorithms, trying to figure out what is our trade space. To do this, we looked at kind of the extremes and the bounds of the problem. So here you're looking at kind of a slice of the Earth, looking at when our receiver is at the maximum latitude of it based on its inclination, what is the relationship geometrically between your specular point and your transmitter? And this kind of geometry problem can help us to find the maximum inclination that we have to go to make sure that we're hitting our latitudes while still being in view of the transmitters that we have to directly contact. So turning this geometry into some plots for trade space, the first thing I want to note is that from looking at this geometry problem, we actually noticed that there's no way to select one single orbital plane that optimally satisfies all of these different requirements. And so we chose to select two different orbital planes that strategically pick out each of the trade spaces for each of the requirements to make sure that everything is satisfied at least once, if not more. So you can see here on this first plot, one of our biggest kind of constraining requirements is the P-band. This is largely due to geometry because MoIST, the only transmitter P-band constellation, is effectively a 0-degree inclination orbit, meaning that to get those high latitudes while still having the reflection of the specular point accessible, you really have to either constrain your altitude or your inclination, primarily your inclination. So for this purpose, we picked a lower inclination, higher altitude orbit, which is what you see here with our orbit plane 2, and this satisfies our SWE P-band requirement. So following on to SWE L-band, you can see here that now our constraint lines have shifted to the point that we can no longer use orbital plane 2 to satisfy this requirement. And so we had to introduce our second orbital plane 1. And you can see here that although only Iridium is visible in this trade space, this orbit has been picked strategically to satisfy Iridium, GPS, Galileo, and GLONASS to get the maximum amount of specular points possible. Moving on to surface soil moisture, you see the same kind of plot, a very similar trade space for similar latitudes and similar altitudes, and our orbital plane 1 still satisfies these requirements. And now you see one of our biggest constraining requirements, which is root zone soil moisture, and you can see here why we strategically picked the 350 altitude for the 80-degree inclination orbital plane 1, and why we picked that super specific 63.5 degree inclination for our 550 kilometer altitude orbital plane 2. So you can see that we're really trying to maximize the number of constellations that are in view for the entire range of latitudes of our orbits. And finally, we see that freeze-thaw, similarly to the other L-band requirements, is met by both orbital planes, which is really good because freeze-thaw proved to be one of the more difficult requirements due to the very, very small grid size. So as you can see here on the right, we've kind of hit all of our major requirements. We have two major planes. Each one fulfills some kind of purpose, whether it's P-band or L-band. And we've tried to optimize to make sure that requirements that can be hit twice are hit twice by these orbits. So just to summarize, we have two different planes. One's at 350 kilometers with an 80-degree inclination. One's at a 550 kilometer altitude with a 63.5-degree inclination. That first orbital plane is really meant to cover all of L-band and some P-band, whereas the second orbital plane is really targeted at making sure that we get good P-band coverage over the entire range of latitudes. And just to see in GMAT, we use GMAT to really propagate both our transmitter and receiver constellations to get orbital ephemeris. And you can see here the difference in inclinations and the way that we've spaced out evenly based on true anomaly. Now, moving on to pole.
Yeah, so for the first order analysis, we were able to determine what more or less our coverage would look like, but we were also interested in figuring out what the revisit would look like. So for that, we developed some code to test the constellation against the mission requirements. The code overlay is kind of shown at the bottom there. So the first thing we do is we propagate the orbits in GMAT, and we store the latitude, longitude points for each satellite for X number of days. Then that gets thrown into a Python script, which solves the asymptotomy problem for each set of transceiver, receiver time step, and we get the specular points from that. With that set of specular points, we can then calculate the revisit and any other relevant statistics that we might be interested in. On the left there, you can see the transmitter constellations that we considered. Basically all the ones that were available, so all of GNSS, Swarm, Iridium, Orbcom, and EOS. Finally, you see our setup for the two different orbital planes that Josh had mentioned. We have currently 10 satellites, and we are biasing it towards the lower orbital altitude because we're interested in having really fast revisits because that's what the requirements have stated. So when we run this code for 10 satellites in two orbital planes for 15 days at a 1 second time step for all the transmitters, we see that we're meeting almost all of the requirements, with free thaw being a big straggler. This is mostly because of the fact that it has a resolution of 3 kilometers, which means that we're missing out on a lot of those grids that are available. In order to fix this, we were really looking to improve this requirement. And so intuitively, the solution would be just to increase the number of satellites that you put up in space, because then you get more coverage. But that's also really expensive. Now, in our opinion, putting up more satellites is effectively the same thing as putting up more antennas. So if we just increase the number of antennas per satellite, we're more or less doing the same thing. So we went ahead and tried to do that, but simulating that in our case was a bit difficult. So we decided to take an approximation of that, and the way we did that is we summed the area of the individual circles into a larger circle and calculated the effective beam width of that larger circle. So in our code, all we really had to do is change that 42 into 56.8 or 67.2 that you see on the slide. When we run that for, again, 10 satellites, 2 orbital planes for 15 days, 1 second time step, for 3 L-band antennas, we see that we actually meet all of the requirements. Freestyle is met at 98%, which we're counting as meeting all the requirements. But moving forward, we'll be using 12 satellites, which we believe will more than satisfy all of these requirements. The reason we do that is for redundancy purposes. So just so you don't get confused in the next slides when we talk about 12 satellites, that's the reason why. The way we're doing that is we're adding 1 satellite to each orbital plane, assuming that one can fail in one plane or the other. And now we'll move on to the data and link budgets with Josh.
So kind of the next step, having selected the number of satellites and our orbital planes and specific characteristics, was looking at data and link budgets. So starting off, just looking at an overview of our satellite block diagram, we've got all of our major subsystems outlined here and really the flow between components of those subsystems. You see fundamentally we're really just collecting data from all these subsystems, feeding that data back into our central command and telemetry unit, and making sure that everything is working properly. I don't want to spend too much time on this slide, so I'll just move on. Kind of zooming out and looking at the bigger picture, we have our satellite block diagram above with all of your basic comms and communications subsystem components. And then kind of to highlight our actual downlinking architecture, we're planning on using the AWS, Amazon Web Services ground station network. We're doing this strategically, primarily for cost, but also for convenience. So we're using the Stockholm and Sydney ground stations primarily because they're at very high and very low latitudes respectively. Since our orbits are both highly inclined, this results in us having a lot of overpasses per day for each of those ground stations. The other really nice thing about AWS is it allows us to use their cloud processing to have really, really nice and convenient post-processing of the data and also transfer of the data to NASA and other customers, as well as kind of an integrated online ground station network that we can use to actually do ground operations and mission operations. Moving on to calculation of data requirements. So the way that we did this was actually backtracking from the requirements and what they actually say. So our assumption here, the 2 big assumptions, is that we are throwing out overlapping requirements. So if we have a singular grid point for freeze thaw that's getting hit 42 times in a day, we don't need all of that data to meet requirements. So we're assuming here that we're throwing out unnecessary data and that we're uploading the Doppler and the TLE and the scheduling to do so. We're also assuming we're throwing out data points over the water, which is a valid assumption. We're also accounting for the land distribution over latitude ranges for each of the requirements to figure out how much of that data can be thrown out. Using all of these calculations, we can get down to a 1.2 gigabyte per day per satellite of data generated. And this is a number that allows us to then determine what our downlink data needs to be. So carrying on to this, you see for our overpass analysis, we've used GMAT. And using GMAT combined with this amount of data per day to downlink, we've effectively calculated we used a 15-day propagation and looked at the number of overpasses of both the Stockholm and Sydney ground stations. The GMAT output, we'd used a Python script to get the averages and got about 9 passes per day. And factoring in a 1-minute establishing connection and closing connection buffers, got about 335 seconds per pass. Using these values, we can calculate what you see as the data rate for our nominal downlink, which is about 3.86 megabits per second. This is assuming a 1.25 compression rate, which is realistic because we used a 1.5 compression rate based on Snoopy and historical experience, but adding a 25% margin to that to account for just margin. So we see that then we used this number and the Jan King Excel spreadsheet, which is a well-established NASA vetted spreadsheet for link budget calculations. In some of the inputs, we use 2 watts of power to the transmitter, which is based on our transceiver and antenna requirements. We're using an AWS provided ground station figure of merit, 10-degree minimum elevation angle, no data encoding, just basic PPSK, and then $10 per minute for wideband reserved AWS ground station usage. So you see here we have 4 major modes that we looked at. The 2 first modes were in nadir pointing, which is our nominal. The patch antennas that we've chosen are low gain, but very high field of view. They have a really wide gain pattern. We did this on purpose to get the most coverage time and for tumbling purposes, which we'll talk about later. But at the half beam width power, we get 3 decibels of gain, and using this 3 decibel of gain, which is a conservative at the outer edge assumption. For that nominal downlink data, we're getting well over 6 decibels for our link margin. For the uplink, we are getting a little bit close with that 5.2 decibel, but we're also assuming a 0.25 megabit per second upload, which is far more than we need for the basic data we're going to be uplinking nominally. For tumbling, you see that we've picked patch antennas that allow us to actually have a 180-degree field of view per patch antenna, but this does hurt our link margin. So we had to downsize our data. This is okay because in a tumbling mode, we're not going to be downlinking all of our data. We're simply going to be trying to recover and save the satellite. So this low gain is kind of accounted for by much lower data rates for simple recovery. So you see there that basically all of our budgets, all of our margins are above 6 and gives us a really, really good recovery capability if we do go into a tumbling mode. And overall, this only cost us $9 million total for that wideband reserved for the entire mission cost, which is much better than near-Earth network. So moving on to subsystem component selection.
So now that we've done our data and link analysis as well as our performance characterization, we can go ahead and select our subsystem components. Starting off with structure subsystem, we have an empty spacecraft 18U chassis with shielding walls, an antenna mounting table, a solar array drive, and a non-pyrotechnic HDRM for decoupling, as well as a 25% mass contingency for additional systems. That gives us a total subsystem mass of 12.5 kilograms and a power requirement of 8.6 watts. Moving on to the TT&C system, we have the S-band patch antenna, as Josh mentioned, as well as the S-band transceiver and diplexer. And we have 3 of each of these. 2 of the patch antennas are going to be mounted in the bottom of the spacecraft and 1 on top. And the second one on the bottom is for redundancy. In a nominal mode, only 1 set of the system is going to be operational, whereas in the tumbling mode, we have 2 sets operational, which will double our power requirement for this subsystem from 14 to 28 watts. The mass of this subsystem is 1.32 kilograms. Moving on to the processor system, we selected the Zephos Q7S, which is a flight heritage processor that's been used on the ISS. It features an ARM dual-core 766 Hz megahertz processor, as well as a real-time clock, and has a 2-watt power draw, and is very lightweight. We paired that with the Delkin Industrial SLC SD card, which is 32 gigs, and we have 2 of those for redundancy, which is the maximum compatible storage for this card. Moving on to the ADCS system, we found in SMAD that a control requirement of less than 1 degree was sufficient for nadir pointing, solar panel orientation, and thrusting orientation. And from that, to have lower than control requirements with a half degree margin, we made a less than half degree margin for our determination requirement as well. We found the Cube ADCS module met these requirements. It's a one-use stack that weighs about a kilogram with a $65,000 cost per unit. It has a 4.5 watts of operating power, and with over 30 flown, it is flight heritage. It boasts 3 reaction wheels, a 3-axis magnometer, as well as torque rods. And when we ran this in the Simulink CubeSat model, we found that the max torque generated over 10 days was less than half of that capable by this module. And in a worst case scenario, we found that momentum dumping could be done once every 2 days by a conservative calculation for nadir pointing. Moving on to the thermal control system, we implemented a thermal control coating and active heating to meet our thermal constraints. Based off of our component selection, our minimum operating temperature constraint was -10 degrees Celsius, and our maximum was 30 degrees Celsius, and those are limited by the battery and prop system respectively. To account for this, we applied a Teflon with aluminum backing for a coating mass over the surface area of the chassis of 0.05 kilograms that has the absorptivity and emissivities listed there. We also included a Captain and flexible heater that has a 35 watt power, but we only use about 20 in the various modes that Paul will present to us in a little bit. And with this combination, we meet our thermal operating constraints with a 5-degree temperature margin. So our spacecraft ranges between -5 and +25 degrees Celsius at all times. From this, we're able to generate our nominal power budget by summing the power of all the respective subsystems. And you'll see that during the day, we use about 47 watts of power, and in an eclipse, we use about 48. Applying a 38% margin to this, we see a day power of 61 watts and an eclipse power of 63 watts. With that power, we can then size our solar panels. We selected the MMA design Hawk solar array, which set up folded for launch and includes a mechanism to roll them out. And it has a gimbal on the roll axis, and yaw will be done by our ADCS system. These arrays are flight heritage since 2017 and are highly efficient. And we found a total solar array area of 58 square meters with a mass of 1.5 kilograms. This allowed us to then size our batteries. We found that with a 30% depth of discharge, our required battery capacity was 136 watt hours. However, for the tumbling safe mode capability that Paul will discuss shortly, we wanted to assume that we could run in this mode for 12 hours. And the required battery capacity for operating in this mode is about 38 watt hours per hour. So with the assumptions you see there, we ended up selecting 6 80 watt hour batteries to meet our requirements for a total power stored of 480 watt hours. And this yielded a depth of discharge of 8.5%, well under the 30% that we needed to meet. Finally, with our power management system to distribute power from the batteries to the respective subsystems, we selected the Endurosat EPS-2. This has lots of output voltages available, which ensures that each subsystem only receives the correct amount of voltage. It has a peak power output of 250 watts, which is well below our highest power load of 101.3 watts, which occurs for 50 milliseconds during prop ignition. This will allow us to calculate our dry mass budget by summing up the mass of each of the subsystems, and that gives us a total of 41.5 kilograms. From the dry mass, we can size our propulsion system. We selected the Dawn Aerospace CubeSat propulsion module, which uses green propellant, and each module has a prop mass capacity of 0.9 kilograms and an ISP of 285 seconds. Performing our propellant mass calculations at both of our orbit planes, we see that at 350 kilometer altitude, we require 2.5 kilograms of prop mass for station keeping. At the 550 kilometer altitude, we don't require station keeping. However, we will require 1.82 kilograms of prop mass for deorbiting, for a total prop mass in the 350 kilometer system of 2.54 kilograms and 1.84 for the 550 kilometer. To meet these requirements, we then used 4 of these modules for a total prop mass capacity in each of our orbit planes of 3.56 kilograms. And we opted to keep the same configuration in both so we could apply the learning curve across the manufacturing for all 12 of our satellites. Now we can have our finalized mass and power budget, where you'll see 315 kilogram mass for the 7 satellites in the 350 kilometer orbit, and 225 kilograms for the 5 satellites in the 550 kilometer orbit, and a total power requirement for all 12 sats at 755 watts. It's useful to look at the entire constellation mass and power of 540 kilograms and 755 watts to compare that to the SMAD estimation. And we find that we're 32.5% below the SMAD estimate for mass and 3.5% below the SMAD estimate for power. And next, Paul is going to discuss our system operating modes.
Yeah, so we were interested in defining different systems for operation, as that helps us define different power requirements. Obviously, not everything is on at the same time, and so it makes sense to kind of have different modes to account for that. You see a really deep overview here. I won't dwell on this. Mostly what I'm interested in covering the fact that we have a safe mode. We have a safe mode in tumbling, nominal operation, which is just for science operations. We have a data transmission mode, and then a propulsion mode. The safe mode is kind of a catch-all mode for us right now, so that'll include launch and any kind of issues that the spacecraft might have. The reason I didn't want to dwell on this, and I do apologize that it kind of shifted a bit, so you can't quite see, but this is the safe mode, is because we have these diagrams that we're reusing. So anything that's kind of highlighted in that color means that the system is on. So for the safe mode, we have the gimbling on for the solar panels because we still want to get solar power. We have the thermal control on. We have attitude control on, and then we have our communications on as appropriate. For the tumbling mode, we turn off the gimbling just because it's probably not necessary at that stage. We need thermal control to keep above our temperature limits. And again, communications is on as necessary. Attitude control is turned off, but we keep the attitude determination on because we need to know whether or not we're actually in tumbling. For the nominal operation, same sort of deal. We have the gimbal on for the solar panel so we can get optimal power. We have the thermal control on. The payload is obviously on as we're taking in data. And the attitude control is on as well since we are trying to be nadir pointing. For data transmission, the big change here is that we turn on the telemetry and command system. Thermal control is not required for this, so that's why you see that off. We can stay within our thermal constraints when we have the TT&C system on. And then finally, we have the propulsion mode on as well. The only thing this has off is the payload, as otherwise that kind of fries our spacecraft if we have that on while we are using propulsion. So that was the purpose of that. Now we'll have a CAD overview with Simon.
All right, so for the CAD overview, before delving into the details, we rendered our CAD and wanted to visualize it in orbit so everyone gets an idea of how it looks when it's accomplishing its mission. Moving on to the actual details of the CAD. So on the top, we have an isometric view with the main external configured components listed. On the bottom left, we have our back view where the thrusters are. So the spacecraft velocity with respect to this screen will be moving to the right. And on the bottom right, we have the bottom view where you can see our three 120-degree spaced L-band antennas, which will be gravity deployed by hinges. You also see our two S-band patch antennas where Josh mentioned already. We have another one for redundancy. And on that note, we have another S-band on top, also with a GNSS antenna for tumbling mode. So we have that omnidirectional view during tumbling. We also have our gimbaled fold-out solar arrays, which will be gimbaled in the roll axis. We have a P-band deployable antenna on the front, like I said, but at an angle to ensure no interference between the Sun-Earth star tracker ports and the antenna itself. We have 4 oversized thruster ports in the back for the 4 1.5U thrusters we selected. And we also have, for our main bus, it's an 18U bus with 1.8 millimeter shielding for radiation. And attached to the bottom, we have a what we call an aluminum table, but it's really only 1.8 millimeters of aluminum with internal supporting structure for the L-band antennas and also for wiring, harnessing, and things of that nature. Moving on to the instruments, the details of the inside. For this, what we were going for is efficiency of use of space, proper configuration to allow for cables, and also for balancing the spacecraft as much as possible by laying everything out symmetrically. So starting on the right, we have more of the front view. We have our science instrument, our 3U science instrument. We have our ADCS module. We have our 3 S-band transceivers and diplexers above the science instrument. And then our 6 batteries are placed, like I was saying before, in a symmetric pattern to try to keep the mass balanced about the center as much as possible. And then on the left, we have the 4 thrusters I already mentioned. And finally, we have our central processing unit, flight processor in the very middle. And now I'll pass on to Ryan for launch vehicle selection.
So now that we know the stowed dimensions of our CAD model, we're able to determine our launch vehicle. And we narrowed this down to two primary considerations. The first choice was the SpaceX Small Sat Rideshare program. This was appealing for its $1.8 million price per launch, where we would need two launches, one for each of our constellations. However, there were some risks that we weren't willing to stomach for this. Primarily, we were unlikely to get the correct orbit, seeing as we wouldn't be the primary payload. It's also a higher risk of schedule delays for this with other payloads. And additional launch constraints would need to be considered in accordance with the SpaceX Rideshare Payloads User Guide. So instead, we opted for the AO-provided commercial FAA licensed launch services vehicle. This gave us two launches at a much higher $14 million price per launch, but it was the lowest risk option with flight heritage launch vehicles. And as the primary payload, we could determine the orbit and launch schedule. NASA provides a launch vehicle performance analysis tool that allowed us to basically plug in our orbit inclination and altitude, and it would spit out the launch vehicles that they'd be willing to provide for us and the range of masses that they're able to accommodate at various orbit altitudes. So for our 350 kilometer orbit plane, you can see where we fall in that chart. And so we are above the range for the Pegasus, but we are well under the mass constraint for any of the Taurus options. Looking at the 550 plane, however, we do fall under the mass requirement for Pegasus, so we could actually utilize the smaller launch vehicle in that scenario. So now looking at our launch vehicle volume constraints, for the Minotaur payload configuration, formerly named the Taurus from the previous slide, that has a capability of 795 kilograms at our orbit, which is way above the 410 constellation mass plus 30% contingency that we have in this plane. And you can see the stowed satellite dimensions labeled in blue to the right and how they all fit in the fairing envelope there. And this would launch from Vandenberg Space Force Base in California. Next, at the 550 kilometer orbit plane, we selected the Pegasus XL with a capability of 350 kilograms. And this would launch from the Reagan test site in Marshall Islands. And that 350 kilograms is over our constellation mass of 293 kilograms, which again includes our mass contingency of 30%. And you can see how the stowed sats will fit with the hold down release mechanisms included at about 10 centimeters in length between each one, and how that still fits within the enhanced payload fairing volume. Lastly, we conducted a vibrational load analysis by determining the fundamental frequency of our spacecraft bus and comparing that to the fundamental frequency requirements of Minotaur and Pegasus, which were 12 hertz and 20 hertz respectively. So using the modulus of elasticity from our chassis material, as well as our spacecraft specifications for area, moment of inertia, mass, and length, we found our spacecraft bus fundamental frequency to be 162 hertz, which meets the requirements for both of these launch vehicles. And now Simon's going to talk about our cost model.
So for our cost model, starting with the spacecraft itself and the payload, we rooted a lot of this in the SSCM, the small satellite cost model developed by the Aerospace Corp. And then within each subsystem we have allocated here, if we found a commercial off-the-shelf component with a defined cost, we replaced the SSCM estimated cost with that cost and didn't apply contingency. But as you can see for other systems such as thermal and structures, we used our mass since we didn't have a defined cost with a 25% mass contingency applied. And that also applies, for our payload, we were given those costs and added those up accordingly to give us a cost for our first satellite of a little under $5 million. And then applying the learning curve, our average cost for the remaining 11 satellites were about $2.5 million. Summing that all up, we have a constellation cost of a little under $62 million. Following that, the rest of the WBS elements we cover are first our launch and the actual support of that, and then our ground command and control, the AWS ground station network usage cost throughout our 3-year mission lifetime, our program level and oversight cost, our ground support equipment for launch cost, and finally our operations cost throughout the 3-year life of the mission. And that finally brings us to a cost of about $120 million for our entire life cycle, which as you can see is well under the $190 million EVM cost cap. Moving on to the specifics of the margins and contingency, you can see it visualized here. Our base estimate of the $120 million is about 63% of the $190 million cost cap. Then we have our contingency stacked on top of that for our 25% mass contingency we applied. and the respective cost increase. And then finally, we have about a very comfortable 28% margin with respect to the $100 million cost cap. Moving on to space environment with Ryan. Pass on.
We did two analyses for the space environment, the first of which was the SPENVIS space debris analysis, where we looked at both of our orbit planes and determined the collision probability across a 3-year mission span with a 5 millimeter diameter debris determined as the catastrophic debris collision size. And we found that across both of our orbit planes, there was about a 0.5% chance of collision. Next, with the Argentic space radiation analysis, with the plots on the right showing radiation dose per year in kilorads, and the x-axis being depth in millimeters, with each of those lines representing historical missions similar to ours, we were able to find the minimum shielding necessary for a 3-year mission of about 1.5 millimeters, with a conservative internal radiation exposure of about 1 kilorad total ionizing dose. And using a 20% margin, we determined that a 1.8 millimeters of radiation shielding on each satellite would be sufficient. Next, I'll discuss our risk overview. Here you can see our risk matrix with a couple of our technical and schedule risks labeled. First being subsystem failure leading to the loss of a single satellite, subsystem failure leading to the loss of three satellites, which would be catastrophic mission failure for us, seeing as we can meet all of our mission requirements with 2 satellites lost. Launch vehicle failure, loss of a MUO satellite, loss of some other transmitting satellite, and for schedule delays, you see system integration and launch as being the 2 delays we considered. Looking at our risk analysis, we found from SMAT a study of 1,600 satellites launched between 1990 and 2008 and found that across 3 years of their launch date, 7% of them failed. And this historical failure rate is broken down by the subsystems seen on the top plot, where thruster and fuel, TT&C, and solar array deployment and operation were the 3 leading causes of failures, and all other failures were about 3%. The consequence, obviously, was the loss of spacecraft in these cases, and I'll read off some mitigations for each of those subsystem failures. For thruster and fuel, we've incorporated a fuel margin, and we have redundant thrusters, as I mentioned earlier. For TT&C, we have S-band antenna redundancy with the 3 instead of just the 1. For our solar array deployment and operation, we have a power margin included there. And for some other failures, we do have additional batteries, a thermal control margin, and an ADCS margin. Looking at programmatic risks, we anticipate a small likelihood of system integration delay, considering that we're using a bunch of commercial off-the-shelf components. And should there be a delay there, we anticipate a small loss of budget reserves. But seeing as though we're using high TRL modular components, we hope to mitigate that. And launch delays historically are quite likely, but the consequence for that would be a minimal loss of budget reserves. And to mitigate that, we opted for the dedicated launch vehicle over the rideshare option. Finally, we were able to calculate a mission success probability based off that same historic study. So with a 7.13% failure across the 3-year mission span, doing a binomial distribution, we found that the likelihood that one of our 12 satellites would fail would be almost 40%. But that 2 would fail would be 16, and that 3 or more would be under 5%. So that's why it's really important that we meet our mission requirements with 10 in our constellation instead of 12, because that gives us a probability of mission success conservatively with this historic analysis over 5%. And just wanted to thank you all for listening, and we'll conclude with our quad chart, and we'll take any questions at this point. Oh yeah, are there any questions online?
Right, so I would like to address the 2 orbital planes that you mentioned, and how did you had a budget for thrust to keep the satellites at the lower plane, which was pretty low, and what kind of life cycle did you estimate that budget of? Oh yeah, 2.5 kilos there, right?
For the lower orbital plane.
Is this
Sorry,
mechanism that you have?
sorry. If I'm understanding the question is, I don't know if you can still see the slides, but are you just asking
Yep.
What this 2.54 is, or what lifetime that is?
Right. Yeah, for life. Okay, to keep it.
Yeah, so that
up there.
2.54 we assumed that we need to be doing propulsion maneuver to get back to 350 kilometers every 15 days. And so that's how we arrived at this 2.54. We got that by
Well,
doing
how long?
3 years.
3
So
years. 3
yeah,
years.
the mission lifetime is 3
That's what
years.
I was.
So that's our
Okay. So that's what I didn't know.
yeah, sorry. That was not clear.
Okay, and this is basically the same bus, just one has the fuel, the other doesn't, or something like that? The same satellite in the two orbital levels, the only difference is that one you put fuel in the tank and the other it doesn't.
No,
Is
so we're
that
using
correct?
the exact same module, even for the propulsion system. So the bus will be the exact same. Likely, what we might do if it comes to that is we just won't fill the tank all the way for the 550
Yeah.
kilometer orbit.
Right. Okay, no, that sounds good. And you mentioned 12, so is this like 6 in each level or 12 in each level?
No, that's a very fair question. Yeah, we're doing 7 satellites at the 350 kilometer orbit, and then 5 satellites at the 550 kilometer orbit.
Oh, I see. Okay, that helps.
Yeah.
Thank you.
More? Are there any more questions online? I don't know if there's.
I might as well weigh in too. My colleague Carlos has asked a good question. Could you go back to your link budget for the downlink and uplink? Let's just talk a little bit about that. So you did it. No, I was talking about, yeah, that slide there. There we go. So what considerations went into your choice for, the threshold for a good link margin? That's really what we're talking about here, right? The stuff in green, and then there's one in orange, yellow. And, what was your thinking along those lines? Why are they good?
Right. So we're shooting for a 6 decibel link margin. This is kind of the standard industry kind of practice, and this is what most low Earth orbit missions aim for. SMAD is kind of the primary source for this data, but we also looked at various both providers of antennas that cited as low as 3 decibels of a link margin being acceptable, as well as some NASA documentation in past missions. So we were shooting for 6 decibels. But from what we've seen, even below 6 decibels, really above 3 decibels is usually good. But we really wanted to have margin here. So does that answer your question?
I guess. So I've done quite a bit of radio work, and I would be marginally comfortable at 10 dB, given atmospheric conditions and things like that. And I would say that, this past few years, we've seen, for example, a lot of smoke coverage and a lot of storm coverage that would really harm your link margin there. So I know that you've got it unencoded with BPSK. Did you consider doing anything a little more complicated to see if you could increase that link margin?
So we actually, yeah, that's
Sorry.
a good point. We applied that 1.25. That's just a standard compression rate for our nominal downlink. But you're right, for the uplink of nominal and the downlink and uplink of tumbling, we did not assume any compression, and we did not look at the data and modulation. But if we do have options to do that, and we can do analysis to try to get those numbers up. One thing I will say is that the Jan King Excel spreadsheet does account for atmospheric gain loss. So I do know it factors that in, but I don't think it's a very high factor overall. So
Yeah, you learn the hard way not to trust somebody's model when you have to deploy things. So just explain briefly, how does compression help?
right. So compression, one of the big drivers that we found here was that really the data rate we were trying to convey is one of the big drivers for this number. We were kind of constrained because we initially were using horn antennas, which had a much, much higher peak gain, but had a much smaller field of view. And this field of view proved really difficult, both in terms of minimizing your viewability of the ground station, as well as for a tumbling or off nadir, like not nominal pointing scenario. So we opted for a lower gain but much higher field of view patch antenna. And so kind of the compression rate was really just trying to get those data numbers down because we had fixed power usage based on the capability of those antennas, and then a fixed gain pattern. And so we were really trying to make the most out of those gain patterns by looking at what is a feasible data amount we can transmit, if that makes sense.
Okay, so I'll just end with more of a suggestion. You might want to look sometime at using either higher modulation like QPSK or something like that with forward error correction. Because if you were to use, especially since you've got a lot of data that's coming down, it's very inexpensive to use something like low density parity check as a forward error correction method, because that, and it just so happens I wrote an FEC based on that on the Q7 processor and tested it with Xiphus, and that runs effectively in real time, so it doesn't hurt you, and
Right.
you can gain a lot more than 3, 4, 5, 6 dB. I can't remember the exact number of your unencoded BPSK, but it's a lot, and
That's
so
really,
a small investment in processing could gain you a lot more reliability. So just a suggestion.
that's
Thanks.
very helpful. What's just a quick question on that? What is the typical additional processing power required to use those higher data modulation levels?
So in terms, I don't know the exact wattage. What I do know is our mission objective for them was 400 megabytes per pass, and we were able to encode that in under 7 seconds of processing time. So that is very low cost per bit, very low. So again, you always have to have the power, right? You have to have the availability, but we also had the ability to spread that processing out in time, because you only cared about it when you got over your antenna, your receiver. So, you know, there were various schemes that we didn't implement, but that we thought about to reduce that. Plus, it was the worst case assumption that all the data had to come down. There was no sort of smarts about it. So it was worst case, and it did work fine. You wouldn't necessarily want to do it for your uplink, because something like LDPC is iterative in the decoding phase, and that is much slower. But when you're getting on the ground, you can process it offline. The decoding doesn't cost you anything.
Right. Okay. Thank you for the recommendation. We'll look into different data modulation options. Thank you. Any other questions online?
Yeah, this is Susan Tower from MMA Design. I'm a little bit curious about your tumbling option. I guess could you describe that a bit more? Because you've got basically a 1 meter sail on the side of your satellite there with the P-band antenna.
Right. So are you asking about like how that would affect our tumbling and how that would affect our attitude dynamics, or?
Well, I'm also not entirely, I mean, depending on how fast you accelerate that, you might lose the antenna.
Right. So yeah, we haven't really been able to do high fidelity modeling of our attitude dynamics. We were able to do, and to an extent, we were able to get the inertia matrix for our CAD model and kind of use that in our attitude dynamics. But it's hard to model how that changes over time. So we did assume. So we kind of were just trying to make sure that we accounted for a tumbling mode, and at the very least had the capability to continue communicating and to try to debug in a tumble. I don't know if you have any recommendations for if we should, like, I don't know, change anything about our design to minimize that risk.
Well, between the solar arrays and the P-band antenna, you're not going to want to tumble very fast. And I don't know if you can control that.
Right. So that actually, I mean, that might help in the grand scheme of things with having a lower torque burden on our reaction wheels. Is that correct? Or
Right. Yeah. But it's an interesting mission op, and it's curious because I have another customer on a bigger antenna asking about the same thing. And of course, we're like, well, it's this great big sail out there. It also might depend on if you can control. I don't know. When you talk about tumbling, it's like it's out of control, but it sounds like you have some control. So you can control which axis maybe you're turning around or something like that. I don't know.
right.
But
Yeah, we do have 3-axis control. Unfortunately, the P-band antenna nominally will be kind of parallel with the velocity vector. So we will have pretty much almost no drag in the nominal pointing, but yeah, tumbling could definitely get some pretty interesting dynamics. So thank you for the recommendation.
Yeah, that's a good problem for the finite element modeling person. Thanks.
So we did look at the Simulink model allows you to input an initial angular velocity rate, like a vector of initial angular velocity rates. We set that to 0, assuming that the deployment from the launch vehicle would be stationary, and then you would have to spin up into a nadir pointing rotation. And that's really looking at the Simulink model. That's where our 1.1 millinewton meter torque comes from, is that initial spin up. It's pretty low, just like momentum, very minimal momentum gain after that. Right. That's good to know. Any other questions online?
Yeah, I just had a couple questions on a few things in your slides. One is it talked about a gravity deployed antenna, slide 48. I just wondered if you could explain what that means. I think it's this one. Yeah, gravity deployed L-band.
So the thought behind that is, or in general, we're trying to go as simple as possible and minimize risk, especially, if, let's say, it was actuated out, that just brings more complexity and risk with it. So we thought we might as well utilize gravity with the weight of these L-band antennas, and maybe a little help from some other component added to the hinge that's attached to the L-band antenna. Sorry, to basically when we're fully out of the fairing and detached from the other spacecraft, these hinges would basically release and drop these L-band antennas into, I believe we determined a 29-degree angle with respect to the aluminum table. And like I said, we're going for simplicity, and we wanted to avoid having to actually mechanically actuate them. Sure, we have not. That would be the next steps, and that should be considered. But if that were the case, if that were an issue, it would be pretty easy fix. We could add a very small servo motor, for example, or something to help it drop out. But regardless, there would be some gravity assist, and the needed help would be minimal, if any.
The other question I had for the packaging in the launch vehicles, the slide 54, this hold down mechanism, is that a product that's provided by the Minotaur, or is that something you have to design?
So actually, I'll go back to a different slide because we did account for the hold down and release mechanism in our structure subsystem. I can go here. So it's the EBAD model 9100 HDRM that we sized there. That's correct. It's a COTS component, and we've included 7 there. Simon, you can speak better on the deployed. Okay.
So in your structural analysis, you really have to analyze the whole stack.
Yeah, more of a structural analysis will definitely need to be done. At this point, that fundamental frequency was all that we were able to accomplish. That was for one individual. So we will need to do way more analysis now that we have the CAD model fleshed out. As we go through and how components are affixed to one another, and look at the whole stack as well.
Yeah, so the way that Jan King does it is basically you input your orbital information. It uses the orbital information to calculate your maximum slant range, And then we input, so another thing actually, I guess for the person who was talking about link budgets, we're using here the gains that are on the absolute edges of those gain patterns. So obviously like 3 decibels is for that half power beam width, which is like the very far reaches. It gets lower to like a 6 or 7 decibel gain at the center of that beam. As well as for tumbling, obviously you're going from -5 up to 3 over the course of like 20 degrees, I think. So yeah, these are worst case gains at the maximum slant range. That was our primary focus, was to really show that if you want to do a tumbling mode, obviously we've seen that that's from historical data in SMAD, that's a really common kind of failure mode, is you either lose attitude control, your solar panels, that you lose some kind of aspect of your system and you start tumbling. And so we really wanted to make sure that primarily communication, we at least give ourselves the opportunity to debug downlink telemetry, try to uplink a solution and try to fix it. So.
Yeah, so true anomaly phasing can be done pretty easily, right? So what we would do is, since we have some extra delta V budget, we would maybe do the station keep and burn a bit earlier for some of them. And so the effects of true anomaly are evened out at that point. There would be some work done there for that, but that's our current model for that. Dean? Yeah. We calculated 22 years. You're right. It does meet the requirements. It does do everything for us. So we could just go without a propellant system on this satellite. We thought it was easier to just include it rather than not. We thought that was a better way to go about it. We could certainly, for example, Dawn Aerospace provides smaller modules with smaller propellant. Like they provide like 0.8 U modules are the smallest they have, and that would have a lot less propellant. Or we could just have one. But something else that we might consider, for example, is if 2 satellites fail on the lower plane, which is more likely. So if that happens, then we can drop one of them to the 350. Okay, well, thank you very much, everyone, for listening.